Hello friends, in the last video we have seen how to write expression for position vector, how to calculate average velocity vector and how to write expression for instantaneous velocity. And this we have illustrated for two-dimensional motion, that is if we have an object that is moving in a plane. Now we will support this video with the theory that we developed in the last video. So this problem says a robotic vehicle or rover is exploring the surface of Mars. The stationary Mars lander is the origin of coordinates and the surrounding surface lies in xy plane. So we have a robotic vehicle often called rover, and this vehicle is trying to explore the surface of Mars. So a lander basically lands on the surface of Mars, and we have to consider this lander as a stationary Mars lander as the origin. So lander is the origin of coordinate system, and the motion of rover happens in xy plane. So this is a two-dimensional motion. So we have to apply formulae concept for 2D motion. Furthermore, the question says the rover which we represent as a point has x and y coordinate that vary with time as follows. So we have to consider rovers as a point. So my rover is a point and this is moving in xy plane. So if it is moving in xy plane in 2D, it has two coordinates. It will have x coordinate and it will have y coordinate. So problem gives you the x coordinate and y coordinate which is as a function of time. So x coordinate is given by this expression and y coordinate is given by this expression. So now the first part of the question is find the rover's coordinate and distance from the lander at t is equals to 2 seconds. So we have to find position vector. And once I know position vector, I can calculate distance from the lander. And lander is basically in this case is origin. And we have to calculate this for t is equals to 2 seconds. But before that, let us analyze situation at t is equals to 0 seconds. So what is happening at t is equals to 0 seconds? So we can calculate x coordinate and y coordinate of rovers. So let us first calculate x coordinate. So we have the formula for x coordinate. So this is the formula. So we have 2.0 meter minus 0.25 meter per second square, and t is equals to 0 I have to plug. So this is 0 second and this is a square. So this is basically 2 meter. Now similarly I can calculate y coordinate. And the y coordinate is given by this expression. If you see, this y coordinate has multiplied by time. Both term in this y coordinate is multiplied by the time. And time is 0. This means this term is 0 and this term is 0. This means y coordinate is 0. So at t is equals to 0, the x coordinate is 2 meter and y coordinate is 0 meter. So this is the coordinate at t is equals to 0 of the rovers. So once I know the coordinate, I can basically write the position vector. So position vector at t is equals to 0, let's write r0 vector. So this is nothing but xi, and x in this case is 2 meter, and the unit vector along the x-axis, that is I cap, plus y component, that is 0 meter, and unit vector along the y-axis, that is j cap. So this is the position vector at t is equals to 0 second. Now let us find position vector at t is equals to 2 second. So how will you find? Once again, you will use the same expression. Only thing is, now in place of time you have to plug t is equals to 2 seconds. So this is 2 meter minus 0.25 meter per second square, and this multiplied by t square, in this case t is 2 seconds, and then this is a square. So if you calculate this value will be 1 meter. Similarly, I can calculate by coordinate, that is 1.0 meter per second times t is nothing but 2 seconds, and then plus, so this is here 0.025 meter per second cube, and this multiplied by 2 seconds raised to the power 3. So if you calculate, this value will come 2.2 meter. So now I know the x coordinate and y coordinate at t is equals to 2 seconds. So x coordinate is 1 meter and the y coordinate is 2.2 meter. So I can write position vector at t is equals to 2 seconds. So let's write r2 vector. So this is position vector at t is equals to 2 seconds. So this will be x component, that is 1 meter, multiplied by the unit vector I cap plus y component, that is 2.2 meter, multiplied by the unit vector, that is j cap. So now I know the unit vector at 2 seconds, that is a position vector at 2 seconds. We can show all this using a diagram. So let's say this is y-axis and this is x-axis. So at t is equals to 0, what is the situation? At t is equals to 0, x is 2 meter and y is 0 meter. So we have somewhere here. So this is 2 meter and the y is 0 meter, and this is origin. So this is the position, that is t is equals to 0 second. Now what is the position at t is equals to 2 seconds? X is 1 meter and y is 2.2 meter. So somewhere here. So this is 2.2 meter and this is 1 meter. So this point is somewhere here. So this point is at t is equals to 2 seconds. So what is the position vector? If you remember, position vector is nothing but you have to make a line from origin to the final position. So this is the position vector at time 0, that is r0. And this is the position vector at time t is equals to 2 seconds, that is r2 vector. So these are the position vector, that is the position of the object corresponding to 0 second and corresponding to 2 second. So questions ask, what is the distance from the lander at t is equals to 2 seconds? So this is the distance. So this distance we have to calculate, that is magnitude of r2 vector is the distance of the rover from the lander. So this is my lander. So lander is here and rover is here. And this is the distance. So this is the position vector. If I take the magnitude of the position vector, that will give me the distance of the rover from the lander. So I have to take magnitude of r2 is nothing but 1 meter I cap plus 2.2 meter, and this is j cap. So I have to take the magnitude of this. So this will be a square root of 1 meter square plus 2.2 meter square. So if you calculate, this will come 2.4 meter. So at t is equals to 2 seconds, the rover is at a distance of 2.4 meter from the lander. And what are the coordinates? Coordinates is x coordinate is 1 meter and the y coordinate is 2.2 meter. So this is the coordinate and this is the distance of the rover from the lander. This is part 1. Now the second part of the problem says, find the rover's displacement and average velocity vector for interval t is equals to 0 second to t is equals to 2 seconds. So we have to calculate two things. We have to calculate the displacement and average velocity between t is equals to 0 second to t is equals to 2 seconds. How will you calculate displacement? If you remember, displacement or change in the position vector basically denotes the displacement, and in this case r2 is the position vector at point t is equals to 2 seconds minus r0, that is the position vector at time t is equals to 0, that will give me the displacement, that is the change in the position vector gives you the displacement. And you know what is the value of r2, this is the value of r2, and we know similarly value of r0 vector. So if I plug these two, we can calculate change in the position vector. So we can write r2 is equals to 1 meter I cap plus 2.2 meter j cap, and this minus 2 meter, this is I cap, and j component was 0, so 0 j cap. So if you calculate this, this will come minus 1 meter I cap, that is minus 1 meter I cap plus 2.2 meter j cap. So this is the change in displacement or change in the position vector that will give you the displacement of the rover. So this is the displacement of the rover. So we can also show this displacement in the same graph. So if you see in this case, this one, that is from here to here, this denotes delta r, that is change in the position vector or the displacement. So this is the displacement. Now we have to calculate average velocity. So if you remember, average velocity is defined as, what is the formula for average velocity? So average velocity, if you remember from the last class, average velocity is nothing but change in position vector, that is displacement, divided by time interval. This is your average velocity. So we calculated change in position vector, that is minus 1 meter I cap plus 2.2 meter j cap, and this divided by, because we are calculating average velocity between 2 second and 0 second. So this is 2 second minus 0 second. So this will be minus 0.5 meter per second I cap. So this is I cap, and plus 1.1 meter per second. So this is 1.1 meter per second j cap. So this is the average velocity we will have between t is equals to 0 and t is equals to 2. So we can also write the same thing, v average is equals to, now this is also a vector. Velocity average is a vector quantity, and the value of this is minus 0.5 meter per second I cap plus 1.1 meter per second, and this is j cap. So this is the velocity vector or average velocity vector between t is equals to 0 and 2 second. So in terms of Cartesian coordinate, I can say velocity vector has two components, one is vx and another is vy, and vx is nothing but minus 0.5 meter per second, and vy is nothing but 1.1 meter per second. So object has two component, that is rovers has two component of velocity, x component as well as y component. This means this is example of 2D motion. So rover is moving in a plane. Now finally the third part, find the expression for rover's instantaneous velocity vector v, and express v at t is equals to 2 seconds in component form and in terms of magnitude and direction. So we have to calculate the instantaneous velocity, expression for instantaneous velocity, and then we have to calculate what is the velocity at t is equals to 2 seconds. We have to express my answer in terms of component as well as magnitude and direction. Now how will you do that? So if you remember, in the last class we said, if you want to calculate Vx, you have to simply differentiate x with respect to time. So this will give you Vx, that is dx by dt. Of course, in this case also, this is a vector quantity. Since I am writing in the x direction, there is no need to put this as a vector because now I am writing in the x direction. Similarly, Vy I can calculate if I take the differentiation of y with respect to time. So let us take differentiation of this term, that is x, and we can calculate Vx. So Vx is equals to differentiation of this constant is 0 and this is minus 0.25 meter per second square, and then I have to multiply by 2t. Differentiation of t square is 2t. If you remember, there is a formula x raised to the power n, differentiation of that is nx n minus 1. So I am using that formula. So if you use that, this will come minus 0.5 meter per second square and then multiplied by time. So this is the Vx. Similarly, I can calculate Vy, which is nothing but dy by dt. So I have to differentiate by component. So this one. So we will have 1 meter per second and differentiation of t is simply 1 and this is 0.025 meter per second cube and differentiation of tq is 3t square. So I can write 1 meter per second plus this is 0.075 meter per second cube and this multiplied by t square. So this is Vx and this is Vy. So once I know Vx and Vy, I can basically write V. V is nothing but Vx I cap plus Vy j cap. So Vx in this case is minus 0.5 meter per second square t, and then I have to put I cap here and then plus this term, that is 1 meter per second plus 0.075 meter per second cube t square. So this is t square and this is j cap. So this is your velocity. So now I know the velocity and it is in the two direction because Vx component is there and Vy component is also there. So we can calculate this velocity at different instant. For example, in this program it is said that we have to calculate this velocity at t is equals to 2 seconds. So let us plug t is equals to 2 seconds. So if you calculate this velocity at 2 seconds, so this will be, so here I will have minus 0.5 meter per second square and time will be 2 seconds in this case and this multiplied by the I cap plus 1 meter per second plus 0.075 meter per second cube and time is 2 seconds, so 2 seconds square and this all is multiplied by j cap. So this all is multiplied by j cap and I cap. So if you calculate all this, this will come, the x component will come minus 1 meter per second I cap and the y component will come 1.3 meter per second and that is basically j cap. So now I know the velocity vector. This is the instantaneous velocity at t is equals to 2 seconds. So what we did, we basically calculated an expression for velocity, instantaneous velocity, and once I plug the value at different point of time, we can get the value for instantaneous velocity or vector for instantaneous velocity. So this is the instantaneous velocity vector at t is equals to 2 seconds. So once I know the vector, I can calculate a speed, that is magnitude of instantaneous velocity. So this is simply nothing but a square root of x component, that is minus 1 meter per second square, plus y component, that is 1.3 meter per second, and then I have to take a square of this, and then finally if you take all this and then take the root, this will come 1.6 meter per second. So the speed or instantaneous speed at t is equals to 2 seconds is basically 1.6 meter per second. Now you can see the velocity has one component that is negative, another component that is positive. So we can show this in this graph also. So this is my x-axis and this is my y-axis. So initially the rover was here, and finally at t is equals to 2 seconds this rover is here. So what is the velocity at t is equals to 2 seconds? So this point corresponds to t is equals to 2 seconds. So it has a component, velocity component, the x component is negative, so this has in this direction, and the Vy, that is positive, so this direction. So what is the resultant velocity? So resultant velocity will come in this direction. So this is Vy and this is the resultant velocity. So we can basically calculate what is the angle that the resultant velocity makes with the positive direction of the x-axis. And if you remember, in the previous class or previous video we discussed tan alpha, where alpha is the angle from the positive direction of the x-axis, is nothing but Vy divided by Vx. So Vy in this case is 1.3 and Vx is minus 1. So this means I can write tan alpha is equals to minus 1.3. So from here you will get alpha is equals to minus 52 degree. Minus 52 degree, this means positive, this is a negative, so this is negative angle. So if you want to convert this into the positive angle, then you have to basically subtract from 180. So this is the negative angle, equivalent to this angle, corresponding positive angle will be 180 minus 52 degree, that is 128 degree. So this means this vector is making an angle of 128 degree from the positive direction of the x-axis, or the same thing I can say this vector is making an angle of minus 28 degree, minus 52 degree, that is the negative side. This is minus 52, so this is the angle minus 52 I can say, or I can say this vector is making an angle of 128 degree from the positive direction of x-axis. Same thing, either you measure the angle from positive direction of x-axis or you give answer in terms of negative, but in that case you have to measure from the negative direction of the x-axis. So we calculated the magnitude of velocity and we also calculated the direction of the velocity. So when we have instantaneous velocity, there are two important things. What is the magnitude? Magnitude in this case is 1.6 meter per second. What is the angle? That is 128 degree is the angle in this case. If you try to compare, if you remember, we calculated average velocity between 0 and 2 seconds, and that was V average is equals to minus 0.5 meter per second I cap plus 1.3 meter per second J cap. You can rewind the video and you can see this expression that we calculated. And the instantaneous velocity, so this is average velocity vector, and the instantaneous velocity at t is equals to 2 seconds that we just calculated, that is nothing but minus 1 meter per second I cap plus 1.3 meter per second J cap. So you see, basically this was 1.1, not 1.3. So you see, the average velocity is not same as the instantaneous velocity. Here average velocity and instantaneous velocity are different. Not only the total, even in terms of each component. Vx of average velocity and Vx of instantaneous velocity are not same. Similarly, Vy of average velocity and Vy of instantaneous velocity is not same. So this illustrates that average velocity and instantaneous velocity are two different things and they will not be equal. So in this video, we explained through a problem how do you calculate position vector. How do you calculate change in the position vector? How do you calculate average velocity vector? And finally, how do you calculate expression for instantaneous velocity? And instantaneous velocity has a magnitude as well as angle, and we can calculate using the formula both the magnitude as well as the direction of the instantaneous velocity vector. And I hope you enjoyed this video, and if you enjoy, please share with your friends, and I will see you in the next video. Thank you.